Hi everybody. Today we're going to finish up what we're working on in Chapter 10, and we're going to look at calculus with polar coordinates. So before we get into the calculus, we need to talk about how we define areas in polar coordinates. What we're going to do is look at the area of a sector of a circle with central angle theta and radius r. So the formula we need is it's 1/2 r squared theta. We're going to use this formula a bunch, as you're going to see. And the reason this is the formula is because the proportion of the circle that is taken up by this sector, it's theta over 2 pi, so that's like the proportion of the angle times the radius. But because the area of a circle is pi r squared, it's the proportion of the circle, its area. And you just simplify and you get 1/2 r squared theta. So now what we're going to do is we're going to look at just any old polar region. We're going to call it R, where R equals f of theta is a positive continuous function, meaning it just can't have a negative radius. And we're pinning it between theta equals A and theta equals B. And B minus A, so when you subtract the angles, it has to be strictly between 0 and 2 pi. If it were 0 or 2 pi, you would get 0 for the integral. So we have to define it this way so we don't get 0. So then what we do is we take this big region and we break it up into subintervals. And the endpoints are these thetas, right? Because we're going around this way. And they're all equal width. They're all delta theta in width, meaning like the angle measure is equal. Well, these rays divide R into n smaller regions, and the central angle is just, here you can see it, for example, theta I minus 1. So we're just saying that you take the entire angle, cut it into n pieces, each one is delta theta in width. And then what we do is we choose a point on the curve in the interval as a sample point, and then this is the sector of a circle because we're choosing it that way. And so we use the formula to compute. This would be just 1/2 r squared theta. And what you end up with is this. So r, so the length of the radius here is a point on the curve. So, and the curve is r equals f of theta, right? It's just some function of theta. So we actually plug that in here. So each of these little wedges has this formula. Well, if we add them all up, we get this sum, right? Just sum from 1 to n of each little wedge. Well, it turns out that if we just take the limit as n goes to infinity, this is a Riemann sum, and we can replace the sum with an integral, which is what we want to do, right? Because we know how to do integrals. And sums are very difficult. So that's the formula we're going to use. We're treating this whole thing as just a sector of some wiggly circle, right? That's what the d theta refers to. So like as the angle moves, the function moves, just like when we have an ordinary integral, when we had x and y coordinates, it'd be f of x dx, right? So y dx. So one of them moves and sweeps out a distance, the other one sweeps out a smaller distance, and that's the integral. So you can use either formula. If you want to think of it as f of theta, that's fine. If you want to think of it as just the radius, that's fine too. It doesn't matter which formula you use. They're equivalent. Again, just remember, the function has to be positive on the interval. All right, so let's do a problem. Let's do this one. So find the area of the shaded region. So this function is just r equals radical theta. And you can see angles-wise, so here's quadrant 1, quadrant 2. So it's filled in quadrants 3 and 4. So we're going from pi to 2 pi. So we just plug everything in. A is the smaller angle, B is the larger angle. R is just the function. And then simplify as much as you can. So the square root squared. I pulled the 1/2 outside of the integral sign. And then the integral of theta is just 1/2 theta squared. So you plug in 2 pi. 2 pi squared is 4 pi squared minus pi squared. And you're done. So other than the formulas being new, it looks just like stuff you've done before. All right, let's do another area problem. This one's slightly more complicated, but not impossibly so. Find the area of the region that lies inside the first curve and outside the second curve. So you're going to want to graph both of these. And you're going to want to decide where that region lies. So it turns out that it's over here. This is 13 cosine theta, and this is 6 plus cosine theta. And the graph shows 2 intersection points, but we don't know where they are. So you substitute one equation into the other and solve. So all I did, I just set the radiuses equal to each other. It should be clear that that's true. At this point here, for both curves, the radius is the same distance. That's why they're intersecting. So I set the radiuses equal to each other. Simplify a little bit. Simplify. So you get cosine theta equals 1/2, which tells you it's plus or minus pi over 3. So when you set up the integral, those are your limits of integration. But we have to talk about how to derive the equation that you plug in. So it's the same thing that you did in earlier sections, like in chapter 5, when you want to find the area between curves, or when you're doing rotations, like the volumes of revolution. It's really a similar thing. So the area of that region is just the area of the big region minus the area of the small region. Right? So if you're trying to figure out where this comes from, just imagine that you start here and you start moving this way. Well, you'd have like almost this whole circle and this little inner part of the circle. So you're just subtracting the bigger outer region and then the smaller piece from that. And you can simplify the formula like this, because everything else is the same. The bounds of integration are the same. They're both d theta. They both have 1/2. So you can combine the integrals together. So it's negative pi over 3 to pi over 3. I pulled the 1/2 to the front. Plugged in the functions. And this is an even function, because this whole, anything squared is an even function, right? So because this is an even function, we can actually use the rule that you can go from 0 to pi over 3 and double the integral. So that's what I did. I just made that a 0 and multiplied by 2. Then I went ahead and FOILed the inside. So make sure you're following along with this stuff. If you need to pause the video, that's fine. Make sure you can do all this stuff. So I just further simplified. So I know how to do this integral. I know how to do this one. We don't have a rule for cosine squared, so you need to use the identity. That cosine squared is 1 plus cosine 2 theta over 2. It turns the 168 into an 84. And then I distributed. And this 84 plus 36 is 48. Went ahead and did the integral. Right, so we have u substitution here, but it's an easy one. You can just do it in your head. Antiderivative of cosine is sine, and the 48 becomes a 48 theta. When we plug in 0, all of these are 0 because they're all sines, so that's nice. And then you plug in pi over 3. And you get 21 radical 3 here, negative 6 radical 3 here, and 16 pi here. Combine it and simplify it, and you're done. All right, let's keep going. Now we're going to look at arc length and polar coordinates. So if you remember what we did in section 10.3, that rectangular coordinates and polar coordinates are related by this. Well, if we treat this as a parametric equation, where instead of t, we just use theta, then we can actually replace r with another function of theta. So x is a function of theta times cosine theta, y is a function of theta times sine theta. And so in order to find the length of the polar curve, first thing we do is take the derivative of both parametric equations. Right, so dx d theta, it's just a product rule, right? So it's the derivative of that times that, plus the derivative of that times that. So this is negative sine, so you get this. And you do the same thing to the other equation and get this. So we have these pretty complicated looking equations, but that's okay. When we plug these into the equations and start solving problems, things simplify pretty nicely. Now that we've taken those derivatives, we need to derive the ds and the arc length formula. So the arc length formula from 10.2 had that big radical with dx dt, dy dt. So we're just doing dx d theta, dy d theta. So we want to figure out what that thing under the radical is going to be when we simplify it. So I just plug in both functions, square both functions, gets pretty ugly here. This is all one thing. This cancels with that. And then we can collect like terms. Right? So we have a dr d theta squared cosine squared theta, a dr d theta squared sine squared theta. So we just factor out the dr d theta squared. And what's left over is 1. Over here we have an r squared sine squared theta and an r squared cosine squared theta. Add those together, factor out the r squared, and you're left with sine squared plus cosine squared, which is another 1. So this thing conveniently simplifies to this, which is really nice, because this is going to be easy to compute, and a lot easier than that in polar coordinates. And so when we take our arc length formula, this is the one from 10.2, we just replace the thing in the radical with the new thing we computed, because this is a lot easier to compute than that in polar coordinates. All right, so let's use this formula. Let's find the exact length of the polar curve from 0 to 3 pi over 2. R equals theta squared. So there's our formula. We're going to need a derivative, so go ahead and take that derivative. So we're going from 0 to 3 pi over 2. Derivative of theta squared is, of course, 2 theta. Simplify as much as you can under the radical. Factor out a theta squared, which when you take it out of the radical becomes a theta. From here, you might look stuck, but this is why we did all that work in chapter 7 a long time ago. This is just a u substitution. And you got to change the limits of integration. Right, so we just plug theta in here, so plug 0 in here, and plug 3 pi over 2 in here, into the equation. So it's just square root of u, and then from the u substitution, we get 1/2 du. So I'm going to go ahead and just simplify all that ugly stuff, bring the 1/2 out front, square this, so you get 9 pi squared over 4 plus 4, and this down here becomes 4. And this just becomes u to the 1/2. So we're ready to do the integral. So you get 2/3 u to the 3/2 with the bounds from 4 to that 9 pi squared over 4 plus 4. Plug in the upper and lower bound. You do not simplify this, just leave it the way it is. this is considered simplified. Even though it looks really ugly, at least we're able to do the integral, right? It doesn't have to be pretty. All right, now we're going to look at derivatives in polar coordinates. To find a tangent line to a polar curve, r equals f of theta, we're going to regard theta as a parameter again. It just helps. And then using the method for finding the slope of a parametric curve and the product rule, we saw this before, that we had, when we did parametrics, we had just had dy dt over dx dt. Well, here theta is our parameter, so we just plug in the individual derivatives here. And this is your formula. This is what you use to do derivatives in polar coordinates. So the curve has a horizontal tangent when dy d theta is 0, provided that dx d theta is not 0, and has a vertical tangent when dx d theta is 0, provided that dy d theta is not 0. If both are 0, we need to use other methods to determine the slope of the tangent. And then there's one other thing that happens. If you're looking for tangent lines at the pole, r equals 0, so which makes some stuff easy to compute. And what it does is it simplifies the derivative just to tangent theta. And again, we cannot take a derivative at the pole if r is 0 and dr d theta is 0. When that happens, we need other methods like a L'Hopital's rule or something like that. All right, find the slope of the tangent line to the curve at the point specified. So a nice easy curve here, 1 over theta. We want to know what is the slope of the tangent line when theta equals pi. So take the derivative. We need it for the formula. And then you just plug this into the formula. And it gets pretty hideous. But you can keep simplifying this. Just multiply through by negative theta squared over negative theta squared. And it simplifies to this, which is pretty nice. Now we just plug in theta equals pi. Oops. And got a bunch of pi's. It simplifies to this. Right, sine of pi is 0. Cosine of pi is negative 1. And you get negative pi. And you're done. So this one works out really nice. So don't be scared by the formulas. Just learn them. And then you'll be good to go for the section. So that's it for what we're going to cover in Chapter 10. If you got any questions, let me know. Here's some more problems to try out. And I'll see you next video. Bye-bye now.